I want everybody to know in TV land that I'm having the students, our classroom, our studio audience move over to this way so that I can be aligned with the camera, so you guys won't feel so left out of the party. So we can all be a happy family. You know what we should do? At the end of the semester, we should have like a pizza party, and then what we'll do is have like virtual pizza or something. I can email you guys pizza coupons, you guys can get pizza, and we can get pizza together, and we can all eat pizza at the same time or something like that, so that we can feel like, you know, it's more kind of togetherness and so forth. Are there any questions? We're actually a little bit ahead. So, are there any questions? I thought maybe I'd ask, maybe you have some questions about the homework problem and the lecture notes, which I'm sure you're reading intently and working on very diligently. Yes?
Is it possible to get an extension on this homework? Can I send it this Monday instead?
Sure.
Thanks.
That was easy. Yeah, which problems are you having difficulty with? Is everybody reading the notes?
Yep.
Is that helpful?
I have some problems in chapter 3.
What kinds of problems are you having?
A problem with some of the equations that is posted there.
Okay.
Yeah.
In the notes?
Yeah, I mean, yeah, I can discuss that with you after the class, maybe.
Oh, okay. Well, I mean, but if you're having the problem, sometimes other people are having them too. But I can. Oh, hold on. I forgot to turn on my microphone. Is that better? I forgot to turn on my microphone. Yeah. Well, let me just scan through some of the problems at the end and pick out a few that might be useful to learn something about. And we'll switch over to the document camera. Let's see. Document camera. Okay. So, yeah. So, this is an important equation here you ran into probably, that it relates the power spectrum. So like let me just go over this a little bit. So for the non-causal case, you have sigma squared non-causal over 1 minus g of omega. So this is the Fourier transform of the non-causal predictive filter response, right? That's going to be equal to the sigma squared of the causal over 1 minus h of omega magnitude squared, right? So, because this is the power spectrum of the AL model, and this is the power spectrum of the Gauss Markov random field. Well, these aren't always equal, but they're equal if the two models are equivalent, right? So then, if you you can multiply on both sides, and you get the sigma non-causal squared times 1 minus h of omega magnitude squared is equal to sigma causal squared times 1 minus g of omega, right? Because I just cross multiply. And if you take the inverse Fourier transform of that, that's when you get that sigma non-causal squared times, now this is delta n minus h of n convolved with delta n minus h of minus n. Now why is that? That's because if I take the magnitude squared, it means I'm multiplying the function by its complex conjugate, right? So the inverse Fourier transform of the function is just delta minus h of n, right? Because that's the inverse Fourier transform of 1 minus h of n, because the inverse Fourier transform of 1 is just delta. So if I take the complex conjugation in the frequency domain is time reversal in the time or space domain. So I get this. So if I convolve a function with its time reverse, I'm effectively getting the correlation. Hi guys, we kind of like decided our new protocol is going to be to try to sit on the left-hand side of the room. And the reason is this, it's like, it's more polite for the off-campus people because the camera's over there. So that way when I look at you guys, I kind of look at the people with the camera also. Okay, so everybody sees where that equation comes from, right? And then if I take the inverse Fourier transform of the other thing, I get sigma squared times delta n minus g of n. So this is the relationship that has to hold in order for the causal and the non-causal models to be equivalent. Well, when does that happen? Well, I mean, if h of n is the finite order causal model, then you can always compute this autocorrelation, and this autocorrelation will always have finite support. So you can always match it in that case. But if someone gives you the non-causal model, you don't necessarily can't find a square root, which is finite. I mean, you can always take the square root of the Fourier transform and then take its inverse. So, you know, you can take the Fourier transform, you can take its square root, and then you can take the inverse Fourier transform, and you'll get something, but it won't be finite order, and it won't be causal. If you impose causality, you can get a finite order, but you know, if you oppose causality, you can get a result, but it still won't be finite order. So now in 1D though, it so happens that you can solve this equation all the time, and the trick is that it requires factoring a polynomial, because you can see how this is basically a polynomial if you took the z transform. Okay. But in 2D, you can't always factor the polynomial, so there isn't always a solution. So that's what this figure is right here. This figure is like, well, if you have a causal predictor, and you took this function, and you took the autocorrelation of itself, you get a function that looks like this. Okay? So this is the non-causal. This is what the non-causal predictor will look like if you have an AR model that's of order P in 2D. In 1D, though, it's simpler. Okay? Does that make sense? Now, and then again, I've talked about this before, but that's the relationship. Okay? Now you can go to you can generalize this to general lattices. So in the general case, you have a thing called the neighborhood system. This is very important. We're going to talk a lot about this later. Where a neighborhood system is, I've been using this notation, but now I've formalized it. In a neighborhood system, you have a pixel S. And then the neighbors of S I denote as this partial S. And the neighbors of S is a subset of all the lattice points. But it has to meet certain conditions. One is that S cannot be a neighbor of itself. Well, that's pretty good. But also, if S are any particular, S is a neighbor of R, then R must be a neighbor of S. So the neighborhood system has to have this symmetry condition. In the causal case, those are not neighbors formally because they don't meet a symmetry condition. Right? So it'd be kind of unfriendly if you live next door to somebody and they say, well, oh yeah, I'm his neighbor, and you say, well, I'm not their neighbor. You know, it's like, well, okay, so if you're going to be, if S is going to be a neighbor of R, then R must be a neighbor of S. Okay? Now we have a concept of cliques. Cliques are an important concept that we'll talk about quite a bit. So if two pixels, if you have a set of two pixels, and if one pixel is a neighbor of the other, we say it's a clique. I call it a pairwise clique, okay? The concept of a clique is more general. So if you have some pixels, okay? Right? So these pixels, you give nodes in a graph, really. And if they're connected, right? Then this is a neighbor of this is a neighbor of this. They're all neighbors of each other. That's a clique, okay? But if I say have another neighbor here, okay, like this, okay, then are all these a clique? No, because this is not a neighbor of this. A clique is a subgraph which is fully connected. So every node in the subclass is connected to every other node in the subclass, in the subgraph. Okay? Does that make sense? Any questions? Okay. So now, so that's a clique, but we're only going to consider pairwise cliques. So you can have a Gaussian Markov random field in the general case is just a vector S, X, okay? Here, it doesn't even need to be on a finite set. It could be on a infinite set, but it would be countably infinite. The uncountable case gets complicated. So, and then the conditional expectation of each pixel is only a function, only dependent upon the neighboring pixels. Okay, so that's the constraint. So if you make the neighborhood everything, then everything is a Gaussian Markov random field. As long as you make the neighborhood big enough, everything's a Gaussian. Any Gaussian random field is a Gaussian Markov random field, as long as you make the neighborhood big enough. But where this definition becomes interesting is when the neighborhood is finite and small, so that you only have a few dependencies. So, and the general concept here, by the way, is this. I'm kind of running out of paper because I screwed up and I didn't bring an extra tablet with me. But the basic idea is this: that you have an image, okay, and you want to model the distribution of the images. Well, first of all, most images are not well modeled by Gaussian. By the way, if you just take an image, I think we did this in E637, but if you want to do it quickly, you take an image in MATLAB, right, and just take the differences between neighboring pixels, and histogram the difference between neighboring pixels. If you look at the histogram, it'll look like, you'll see the histogram will look like this. It'll be pretty heavy tailed, with like a Laplacian distribution. So each of these sides will be are reasonably well modeled by exponentials. It's amazing that you can take pretty much any natural image. I mean, I'm sure if you really, like if I say that it always works, of course, then as graduate students, I would be disappointed if you didn't go out and desperately find an image that was an exception, okay? I'm sure that you can take a picture of something in the natural world where it won't be true. But okay, so you guys should actually do this, okay? To show you how enthusiastic you are about this class, okay? So you go out and take a picture. It's a good exercise to do. In MATLAB, it shouldn't take you more than 16 minutes. Take neighboring pixels, take the absolute value, or take the just magnitude value, and plot a histogram. You'll see it falls off. It doesn't look Gaussian. It's pretty closely modeled to Laplacian, and it's pretty accurate model for a wide variety of images. I'm sure if you find something, you could find some kind of image in the world for which it's not, which is Gaussian, but you'll be fairly hard pressed. I mean, for most natural images, it will be pretty accurate, okay? And because the edges are really heavy tailed, and there are edges naturally occur due to the occlusion of light in natural images. So, okay, so one thing is they're not Gaussian, okay? Hold that thought. We'll come back to it later. But the other thing is this, there's dependencies. Clearly the pixels are not independent, right? There's a lot of dependencies. As a matter of fact, there's very long-range dependencies in the images. So how do you model that? Well, one possibility, let's say we're going to assume that the image is Gaussian. Well, you could assume that, okay, you're going to have the covariance, so it's normal, would say, I don't know, some mean, let's just say the mean 0 to make it simple, okay? And some covariance R, right? And R is dense. It's a huge matrix. So then what you say is every pixel is dependent on every. Well, actually, if you take a real image and you compute its covariance, R really is dense. Because what's going to happen is that, if you take two pixels even relatively far away, the autocorrelation is going to remain significant over long distances, right? Because, if you're in a bright region in the image, then, pixels could be pretty far away, but if one's bright, the other one is likely to be bright also. right? I mean, like, it could be, because you have slow, like, if I took a picture of this room, and over there I got the blackboard, and I have the wall. Well, if one pixel's in the blackboard, you have to go pretty far away before it's not in the blackboard anymore. So pixels will be correlated over a very long distance. So if you compute that covariance matrix, first of all, the covariance matrix is huge, right? Let's say it's a million pixels, which isn't a particularly big image. Then the covariance matrix R is going to be a million by a million, right? So that's 10 to the 12. Okay, 10 to the 9th is a billion. 10 to the 9th is a billion, right? So
1,000 billion?
it's 1,000 billion, right? So it's a trillion. So, okay, a billion is a tera. So this is, a billion is a giga.
Yeah.
So this is a tera word of storage, okay? So, let me see. If you want floats, well, in MATLAB it's always doubles. You have to have doubles, right? So how many bits are in a double? 64. In fact, if you think about it, the newest architectures are all 64-bit, right? So they operate, they might have addressing modes that will actually read the 32-bit number. I'm not sure, I'm not a computer architecture expert, but mostly they like to read 64 bits at a time. That's the bus bandwidth anyway. So, 64 bits is how many bytes?
8 bytes.
It's 8 bytes, right? Because, you know, you guys are better at math than I am, so you know that 64 divided by 8 is 8, okay? So they're 8 bytes, okay? So, storing this thing would require 8 terabytes TB of storage. I mean, you know, it's ridiculous. Just to store one matrix. You haven't even started the problem yet, okay? So this is a really big covariance matrix, okay? But somehow it seems like there should be a better way of doing this. Well, what you do is you say each pixel here is really only dependent upon its neighbors, right? And now what happens is you don't really need R, you instead compute R inverse. R inverse is this matrix B. B. Okay? Now, let's go look at this. This is where the magic occurs. So, we have, now what's B? B is this matrix right here. And B is given by, this thing is G. Okay? So this gamma thing is a diagonal matrix. So that's just a scaling factor. So if I'm looking for the values of B that are non-zero, which values of B are non-zero? Okay, so the diagonal is non-zero because it has one constant. Okay, so the diagonal is non-zero. What else is non-zero? This is really important.
I think only diagonal here.
So is it only, so B is a diagonal matrix? B is diagonal. Is I diagonal? Is D diagonal?
No.
No, D's not diagonal. What's D?
It's non-causal, so there are going to be
Yeah, it's a non-causal prediction matrix. So which elements in there are non-zero?
all elements except for the diagonal.
All the elements are non-zero?
Except for the diagonal.
Except for the diagonal, is that correct?
One should actually use for prediction.
The ones, so which ones are those?
Neighbors.
It depends on the size
The
of
neighbors.
Basically, the off diagonal.
The non-zero elements of G are the neighbors, right? So is B mostly all zeros or mostly not zero? What's zero? What's not zero?
The diagonal is not zero.
Yeah,
The diagonal is not zero. We've established that.
The diagonal is 1, and then all the neighbors,
It's
so it's
not
diagonal
one,
and
but
neighbors.
it's close to one because
It's 1 over
Yeah, it's just a scaling.
Yeah, because of the scaling.
And then the off diagonal is not.
It's actually not even close to 1, but it's intellectually close to 1. Yeah.
That's what depends on the neighborhood, more the number of.
It will have the same non-zero pattern as G.
Yeah.
We will have the same non-zero pattern as G.
Right. So you're both saying something that's true, but it's a little bit different. So maybe both say it. So, well, say it out loud. Like, be proud of your opinion, even if they're wrong.
You'll have like the same
Smaller the size of the neighborhood, more will be the number of zeros in B.
The smaller the size of the neighborhood, the more zeros there will be in Z. So the number of non-zero elements in G is kind of proportional to the number of non-zero elements in B, right? Except for the diagonal. Right?
Yeah.
So what does it mean if an element in B is 0? Does it mean they're not correlated? Oh my gosh. I'm gonna like go fishing here. I'm gonna really get in on this one. So that was good because you said exactly what I wanted you to say. Okay? I pulled you into my web. Okay, so that feels that way. What you're saying feels true. Okay, but is it true?
No,
No, it's not true. Why?
it's a precision matrix, it's not the.
Because this is the precision matrix. This is not the covariance matrix. So an element of B can be 0, but those two pixels can still be correlated, right? So what is true?
It doesn't matter. That's
So it doesn't matter. Nothing matters.
because you're not using it as.
It's Friday, so.
Actually, the lambda inverse is just like an identity matrix with a scaling factor. So it's identity.
Gamma. You mean gamma. You said you mean gamma, right?
So identity into identity. Identity into matrix is the same matrix. It's I minus G again.
So this is just a scaling factor,
Yeah.
okay? So let me draw this, okay? By the way, the discussion we're having
So we'll have
is
like,
very important here, okay?
we'll have one of the diagonals and all the other elements of G will be the same.
So this is B. Let me see. So we're going to have, the equation is here is, I'll go wider angle a little bit. Okay, so the equation is this. This is, by the way, a homework problem, and it's very important. Oh man. Okay. Okay. So we have here that the basic equation here is that D equals this gamma inverse times 1 minus D. Now this is just a diagonal matrix, so it looks worse than it really is. Okay. So I'm going to draw this. So you're going to have here, this is a matrix, and it's B. Okay, this is B. Okay, this is B. Okay. Now, the diagonal, I'm almost like not worried about it from the point of view of whether something's 0 or not, because the gamma here is diagonal, and its elements are all non-zero. Why do the elements of gamma have to be non-zero? Any thoughts about that? What are the gammas? The gamma section has an interpretation.
Gamma is the variances, prediction, the variances of
The gammas are the conditional variances, the conditional prediction variance for each pixel, okay? By the way, what I'm teaching you here is actually really useful, okay? Not just in image processing, this comes up in all kinds of applications where you have to look at multivariate data. This gamma here this is the covariance test. The covariance is the prediction error, right? And the diagonal of the prediction error variance is gamma. That's what gamma is. It's just a diagonal matrix of non-causal prediction variances, okay? So the prediction variance can't be 0. Why? it's sort of a technicality, but
Because the random variables, they have variance invariance.
well, okay, because if the prediction variance was 0, it would mean that the covariance was singular. See, if you can find a linear transform of this data vector, which is 0, then there must be a 0 eigenvector in the covariance. I can prove that for you. That would be a simple thing for you to go prove. You should do that as a homework problem, okay? So, in other words, if I can find any linear combination of a jointly Gaussian random vector whose variance is 0, then it means that there would have to be an eigenvalue of 0 in the original covariance matrix. And I precluded that. I said that by definition said for any jointly Gaussian random vector that the covariance has to be positive definite, okay? I did that to avoid all the nasty problems that could happen if the covariance matrix is not positive. Otherwise, what you're telling, because then there's no density function, right? Because then I could have I could say 3 is the Gaussian random variable. Its variance is 0, okay? So I want to avoid that nasty case, okay? So I constrained the problem, I laid down the law, okay? That if I say it's a jointly Gaussian random vector, it means that it must have, its covariance cannot be singular. It has to be positive definite, okay? So since the covariance can't be singular, that means these gammas, none of them can be 0. Another way of looking at it would be the diagonal elements of gamma just multiply the rows of this matrix here, right? Okay, if you multiply by you have this is gamma 1, 1, and this is gamma, say, n, n. So I use uppercase N. And these are all zeros, right? If I take that matrix and I multiply, and this thing here is I minus D, right? So, just, if you take a diagonal matrix and you multiply, all you're doing is each element is diagonal, just multiplies the corresponding row of the matrix, right? Everybody good with that intuition, right? That's just getting, this is like one of those things when you're doing linear algebra, you just get used to this, right? If you take this and you just go, zoom, okay? And each row, the sound effects make it easier to understand, by the way. So, you go here and you go, it's sort of like, how, well, okay, the smells of Christmas. Well, it's the sounds of matrix multiplication, okay? You get this thing and you go, zoom, like that, okay? When you go zoom, each corresponding element multiplies that corresponding row of the matrix, right? So this is just a fancy way of writing I'm going to scale the rows, okay? And the scaling factors can't be 0 because the determinant of B cannot be 0, right? B is the inverse covariance, so if the covariance is not singular, certainly its inverse cannot be singular, okay? So if any row were 0, clearly the matrix would be singular. It's a square matrix. If it has a row of 0, I can easily find something to multiply by, which is 0, so its null space is not empty, okay? Or the null space, is not empty, right? So, okay, so you good with that? So basically, you can sort of ignore this. This is a very complicated way of just saying you can ignore it. These are individually the prediction, non-causal prediction variances, okay? Now what happens here? Now, so the B's, okay, I know that, first of all, B is a symmetric matrix. Its diagonal is gamma 1, 1 through gamma n, n, right? Okay? And then there's going to be some stuff going on out here, okay? Now, the interesting thing is this. What's going to be not 0? In one dimension, it's easier to think about this in one dimension, but in two dimensions it's similar. So in one dimension, it was only the next door neighbors that were, if the neighbors were only the points next door, okay? Then this would be tridiagonal. And these would all be 0. So, the non-zero elements of B, okay, represent the neighborhood relation. So so B ij, okay, is not equal to 0 if and only if I is a neighbor of J or I equals J. Those are the only two ways that if the element of B is not 0, that means that I and J are not our neighbors. Or you're on the diagonal. So this is just a way of encoding the neighborhood condition. Alternatively, if B and ij is 0, then what does that mean?
They are not neighbors.
They're not neighbors, okay?
The non-diagonal elements of B, they're just the non-zero elements of G.
Yes. So let me say this again. So Gij is not 0, okay? If that's not 0, that means I is the neighbor of J. Because remember, what is Dij? Dij is just the prediction coefficient of between I and J. Okay, actually it's the prediction coefficient, I think, of J for pixel I. Okay, and in the so here right. So I think the way we wrote it is that I'll just write it here actually that I'm writing here FR. I use S and R to emphasize that it doesn't have to be one dimension. It could be a graph. Okay, and that's equal to GFR. I use a lowercase and uppercase because I don't know, because this is a matrix and that's sort of a function. It's, I'm trying to keep it clear. But does that make sense now? This is a very important point. And hopefully, if you read the notes before you came to class, this makes sense to you. Okay? Because once you understand this simple point, there's a lot of stuff that's going to become much clearer. Okay? So everybody gets this?
Yeah. And it's true that the zero portion doesn't matter, right? That's what I meant last time I said.
Well, okay, what do you mean by doesn't matter?
Well, it's not in the influencing positions. For the G matrix.
Okay,
they're not in the neighborhood of...
They're not in the neighborhood. That's true. Okay, so B here is sparse. What do I mean by B is sparse? Well, I mean that the only non-zero elements of B, for all intents and purposes, are the neighbor pairs. Okay? Every non-zero element of B is a clique or a diagonal element. Most diagonal elements are only n points. So if you have, say, 4 neighbors per pixel, then how many non-zero elements are going to be in B? Well, it would be just 5 times n. So this is sparse. Most of the entries are 0. Usually. The number of non-zero entries, if you have a fixed neighborhood, so if there are a constant number of neighbors for every pixel, then the number of non-zero entries is proportional to n. But the number of entries in B is proportional to n squared. There's a big difference between n and n squared. If n is 1,000,000, then I'd much rather deal with 5 million elements than 5 trillion. Okay? 5 trillion is much bigger than 5 million. It's 1,000 times, it's 1,000,000 times bigger. Okay? Right? So it's a difference. It's not a small difference. It's 1,000,000 times larger. So this matrix is huge, but mostly it doesn't matter that it's huge. Because, okay, yes, it's got 8 terabytes of storage, but most of the entries of B are 0. B is sparse. You only have to store a little bit of it. Okay? is R sparse? R here is equal to V inverse. Is R sparse? No. R is not sparse. R is dense. So B was sparse, but when I take its inverse, nasty, horrible things happen.
Yeah, but the R is the covariance matrix for the prediction errors. Is not the
No, R is the covariance matrix for the actual data.
But in the data independent.
No. So, let's go back. By the way, the questions you're asking are beautiful, okay? Because this is precisely the thought process you need to go through, okay? To really understand this. X is the thing we're trying to model, so that's the image, okay? G's are the prediction filters, the non-causal prediction filters. That's sparse, because for each element of X, we're only going to use a few elements, other neighboring elements to do each prediction, okay? G is the precision matrix, so that's also going to be sparse, but the actual covariance is B inverse. When I take the inverse, that will be the covariance of X. The inverse will be dead. So, this is the magic of Markov-random fields and why they're so important. Because we're sort of getting something for nothing. And we're getting not just a little bit of something for nothing, we're getting something huge for nothing.
So in the non-causal case, all the random variables, they'll always be like dependent on each other? I mean,
so this is true of both the non-causal, yes, and the causal case. But let's look at the non-causal first, so we don't confuse ourselves, okay?
But in the causal case, we read that the prediction errors were independent and so were like the random variables.
No, the prediction errors are independent, but the random variables are not, okay?
Just
a
a follow-up question. In the causal case, we saw that the predictions were also independent of the data, of the previous
of
data.
the past data.
Yeah.
But not the data are not independent of each other.
That's correct.
Only the errors are independent of the previous data, and the errors are independent of the previous errors.
Yeah.
For the causal case.
Yeah.
Okay.
Now, in the non-causal case, the errors are not independent of each other,
They're correlated.
and the errors are actually not independent of the data either. Okay. So, so the upside here is our objective here is to model complex phenomena. Okay. And modeling, and the name of the game is parameters are bad. Okay. The more parameters you will have, parameters are bad in two very important ways. First, they're bad because, the model is just more complex, okay? But they're especially bad because you always have to estimate parameters. And the more parameters you have to estimate, the harder it is to actually fit a real model to any data. That's why we always want a sparse model, a model that has the fewest number of parameters, okay? So, this is a dramatic reduction in the number of parameters. We've gone from, how many parameters are there in a general covariance matrix? How many degrees of freedom? Well, the matrix is symmetric, right? So it's not quite, it's actually going to be like, it's n plus n squared minus n over 2, okay? Because the number of elements in the matrix is n squared. You subtract the diagonal and you divide by 2, and then you add the diagonal back. So this thing equals, let's see, it's going to be, so it's going to be n times n plus 1 over 2, I think is the way it works out. So it's basically order n squared. But how many parameters are in B? Well, let's say that every pixel has k neighbors. And let's say that you also need a diagonal element. The diagonal element is the prediction variance. So if there are k neighbors, then what is it going to be? It's the number of parameters is going to be n times k plus 1. That's going to be a much smaller number, because if this is 4, it's going to be 5n, and this is going to be n squared over 2, basically. So if it's 1 million, this will be 1/2 terabyte, okay? And here it'll be 5 million. So it's a dramatic reduction in parameters. And in fact, that would be even, if the prediction filter is not a function of position, then there might only be k plus 1 parameters. So you have, say, 4 neighbors plus, so you have 5 parameters. You've gone from 1 trillion parameters to 5, okay? And but you've retained correlation. So if 2 pixels, okay, so this gets me to my point that I wanted to ask at the beginning. It's very important. If the 2Bij, if the entry of Bij is 0, okay, this is the question. I'm sorry, I forget your name. What's your name? Rahu. Okay. He made a point. He was very kind to say something which was false. Okay. But you said exactly the right false thing. Okay. You said if the B is 0, the pixels are uncorrelated. Is that true? No. They could be highly correlated. Okay. Because when you take the inverse covariance, they could be highly correlated, but they're not neighbors. That's the power of this model. You have local interactions. You have local interactions only in the neighborhood, but you have global dependencies. It's a very powerful thing. It's like, it's like you can use. It's like having a 50-foot long fishing rod, and you can go, and over here you can with this little thing, you have this gigantic lever. You can control these little parameters here, and you control pixels that are thousands of pixels away. Okay? So, it's a very powerful model. Okay? That's why people like Markov random fields. Okay? So, and you can do this not just for an image, you can do it for any graph. And these equations always hold. Right? So I want to go through these. If you go look at these problems are explaining essentially this, okay? They're asking you to work through simple problems that have you understand this, okay? So one of my things is, okay. So, okay, we can work. Do you have any questions about these? Some of these are, oh yeah, here. If F denotes the neighborhood system of NRF, then show that if R is not a neighbor of F, and R is not equal to F, then this has to be 0. Now you know the answer to that, right? Why? Well, it has to be 0 because if they're not neighbors, then the entry in G is 0. If the entry in G is 0, then the entry in B is 0. So people spend hours working on this. It's like a 5-minute proof. 5 minutes. It's a 10-second proof. Okay? There's a lot of problems in here that are easy, really easy if you understand them, and monstrously difficult if you don't. Okay, show that we can define a valid neighborhood system. Oh, okay, so we just take all the B's that are not 0, and so if a B's not 0, then we make that our neighborhood. Okay? So if someone gives you the inverse covariance, the precision matrix, and they ask you to define the neighborhood, it's easy. You just find the points that are non-zero, right? That's what this is telling you. Okay, determine the inverse covariance in terms of G and gamma. Oh, okay. Yeah, well, we always know how to write V in terms of G and gamma. It's trivial. All right? They correspond to a valid Gauss-Markov range. Okay, so what are conditions? Well, gamma. Okay, so what are the conditions? Well, gamma has to be a diagonal matrix with positive entries. because the prediction variance can't be negative, right? And D has to have a property. Well, okay. The entries. What are the conditions on D? Well, the conditions on D actually are that. Well, basically, the condition is that. Well, the diagonal has to be 0, right? But then, and the entries which don't correspond to neighbors have to be 0. And now the other condition is that the determinant of I plus D has to be non-zero, right? The determinant can't be 0. As a matter of fact, I think the eigenvalues. I want to say the eigenvalue has to be positive. Oh, I'm sorry, this is 1 minus. Yes, minus. Yeah. But anyway, I'll let you think about that. Right. And also, it has to be symmetric, right? The gamma times 1 minus D has to be symmetric. Right? So this has to be positive definite, so this is to be B, right? This is got to be positive definite, and it has to be symmetric. I don't think there's any simple way of enforcing those conditions. But, so in this case, for that time, I just want you to say, okay, this matrix has to be positive definite and symmetric. All right. And let's see, let me see, what else we have here? Yeah.
Is B an exact inverse of R?
R? Yes, by definition. B is the precision matrix, so it's the inverse of R. So this is really important because, like in a lot of problems in multivariate statistics, you'll have a matrix R inverse, right? And now you'll know, oh, now I can look at that matrix R inverse and I understand a lot about the problem. When I can see the non-zero entries are the things that would be the neighbor, which is to say that they would be used in a non-causal predictor. And the zero elements, they can correspond to pixels that are correlated, but they wouldn't be neighbors. Okay? And let's see. Okay. So is this true? Is it true that the joint probability distribution is the product of the conditional probability distribution of pixels given their neighbor? This is good. Is that true? If it's true, prove it. If it's not true, why isn't it true? Any thoughts?
Because they are correlated.
The answer is this is not true. We're kind of running out of time, so I'm just going to say it. It's not true. For the causal case, we could take P of n times P of n less than n, right? And then P of n minus x of n minus 1 times x of less than n minus 1. And we could keep changing ourselves along, and this would be a way of calculating the probability, right? When we have Markov chains, we'll see that's how you do it. But here, you have loopy dependencies. So that's false. It's interesting, in the early days of Markov random fields, people just pretended that was true even though it wasn't because they wanted something to be true and they weren't sure what was, okay? But what you can do then, sometimes people will call that the pseudo-likelihood, even though it's not really the likelihood of anything. And then you can estimate parameters. One of the really fundamental problems we're going to run into with Markov random fields is it's hard to estimate parameters. And the reason it's hard to estimate parameters is that normalizing constant z does not have closed form for the Markov random field. In the causal case, it had closed form because the determinant was 1. But because the determinant is not 1, it doesn't have closed form, and it's hard to estimate parameters. We'll see later. Okay? Those are problems and read the notes. Okay? Bye.